In 2025, global nuclear arsenals contain approximately 12,300 warheads, an unprecedented destructive capacity that still pales compared to the natural forces that shape our planet. But here's the question keeping scientists awake at night. What happens when unstoppable force meets a movable object? Specifically, what happens when a 50-megaton hydrogen bomb meets 1,100 atmospheres of crushing ocean pressure at Earth's deepest point? You might expect massive tsunamis, cracked tectonic plates, maybe even knocking Earth off its axis. Research on underwater explosions reveals that deep detonations produce only small surface waves. The reality is far stranger, and it involves a nuclear fireball that expands and contracts like a deadly balloon, defying everything you think you know about explosions. But first, we need to understand exactly what weapon we're dealing with: the Nuclear Heavyweight Championship of 2025. In 2025, 9 states hold approximately 12,300 warheads, 88% split between the US and Russia, while modernization focuses on sub-5 megaton, multiple warhead missiles, and hypersonics, favoring precision over yield. This represents a fundamental shift from the Cold War arms race that gave birth to history's most ridiculous weapons. Modern nuclear powers have largely abandoned the megaton madness of the 1960s. Russia's newest RS-28 Sarmat intercontinental ballistic missile carries multiple smaller warheads instead of one massive bomb. The United States has upgraded its Minuteman III missiles with precision-guided warheads that pack around 300 kilotons each. China's growing arsenal focuses on mobile launchers and hypersonic delivery systems that can change course mid-flight. These weapons represent a fundamental shift in nuclear strategy from raw destructive power to surgical precision. The physics behind this evolution makes perfect sense. A single 50-megaton bomb creates a fireball roughly 6 kilometers wide. Nuclear engineers discovered that splitting massive warheads into smaller ones actually increases total destructive capability while reducing the radioactive fallout that makes territories uninhabitable for decades. This efficiency revolution explains why nobody builds weapons like the Tsar Bomba anymore. The Soviet Union's RTS-220 hydrogen bomb remains the largest nuclear weapon ever detonated, releasing 50 megatons of energy with a 6-kilometer fireball. In October 1961, the explosion registered 5.25 on the Richter scale, shattered windows 900 kilometers away, and produced a mushroom cloud that reached 64 kilometers into the stratosphere. Despite representing the absolute pinnacle of human destructive capability, the Tsar Bomba was actually a terrible weapon. It was too heavy for practical military use, too large for existing missiles, and produced so much radioactive fallout that it contaminated vast areas for decades. But here's where things get interesting. For our thought experiment, we need this level of overkill. We're not testing whether a nuclear weapon can damage the ocean floor. We're testing whether the most powerful nuclear weapon ever built can make any meaningful impact on Earth's most extreme environment. We're essentially asking, what happens when humanity's greatest achievement in raw destructive power meets nature's most imposing defensive barrier? The physics of underwater nuclear explosions work differently than surface detonations. When a nuclear weapon explodes in air, the fireball expands rapidly because the atmosphere provides relatively little resistance. The explosion pushes outward in all directions, creating the characteristic mushroom cloud as superheated gases rise into the sky. But underwater, the weapon faces a completely different set of physical constraints that fundamentally alter how the explosion behaves. Water is roughly 800 times denser than air, which means it takes significantly more energy to displace the same volume. Additionally, water doesn't compress nearly as much as air under pressure, so the explosive force encounters immediate resistance from the surrounding liquid. This resistance grows exponentially as the explosion tries to expand, creating a unique dynamic between the weapon's energy output and the ocean's massive inertia. Research on deep-water nuclear detonations reveals that underwater blasts create approximately 1-kilometer cavities instead of the 10-kilometer expansion seen in air. This fundamental difference in bubble formation physics shows how water pressure dramatically constrains nuclear explosions, forcing the fireball into a cycle of expansion and contraction as it battles against the surrounding liquid. The question becomes whether 50 megatons of explosive energy can overcome crushing water pressure. It's like asking whether a sledgehammer can crack a diamond or whether a firecracker can topple a mountain. The answer depends entirely on understanding how these two forces interact at the moment of detonation. So we're about to witness the ultimate heavyweight championship match, humanity's most destructive creation versus nature's most extreme environment. In one corner, we have a hydrogen bomb that could theoretically vaporize Manhattan, level every building within a 35-kilometer radius, and irradiate thousands of square kilometers of territory. In the other corner, we have crushing water pressure that can flatten titanium submarines and compress human bodies into nothingness. The nuclear engineers who designed these weapons essentially told physics to hold their vodka while they pushed the boundaries of what fusion reactions could achieve. They crammed together isotopes of hydrogen under conditions that replicate the core of the sun, then wrapped the whole thing in a uranium tamper that reflects neutrons back into the reaction to squeeze out every last bit of energy. The result was a weapon so powerful that its designers couldn't even test it at full capacity without risking global environmental consequences. Military strategists realized that nuclear weapons work best as deterrents, not as actual battlefield tools. The goal shifted from building bigger bombs to building smarter ones that could penetrate enemy defenses and strike precise targets. This brings us to our central question. If modern nuclear weapons have moved beyond the megaton monsters of the past, why are we using the Tsar Bomba for our underwater experiment? The answer lies in the weapon's sheer absurdity. The Tsar Bomba represents peak nuclear engineering, the moment when humans decided to see just how much destruction they could pack into a single device. The results will challenge everything you think you know about nuclear weapons, ocean physics, and the relationship between human technology and natural forces. Our 50-megaton hydrogen bomb might be capable of destroying entire cities, but the ocean has been absorbing asteroid impacts, volcanic eruptions, and tectonic collisions for billions of years. Something tells me this fight won't go the way most people expect. But not just any ocean location will do for this ultimate test. We need the most extreme underwater environment Earth has to offer. Challenger Deep, Earth's final boss level. Challenger Deep represents the most extreme environment Earth has to offer. The Mariana Trench isn't just deep water. It's an alien world that exists right here on our planet, complete with crushing pressures that would instantly flatten any human body and temperatures that hover just above freezing. The latest 2025 measurements place Challenger Deep at 10,935 meters below sea level, making it deeper than Mount Everest is tall. Recent expeditions using advanced submersibles have revealed that our understanding of this underwater canyon continues to evolve. The Chinese Vendu submersible reached depths of 11,000 meters in 2020, collecting hundreds of biological samples and updating our knowledge of what actually lives down there. These missions have shown that the trench stretches approximately 2,550 kilometers long and averages 69 kilometers wide, creating a massive underwater scar across the Pacific Ocean floor. The pressure at the bottom of Challenger Deep reaches 1,100 times greater than at sea level. To put this in perspective, imagine having 50 jumbo jets stacked on top of every square meter of your body. The water pressure alone exerts 16,000 pounds per square inch, which means that every square inch of surface area faces the equivalent weight of a small car pressing down on it. This pressure is so intense that it fundamentally alters the behavior of matter itself. Steel submarines designed to withstand enormous forces crumple like empty soda cans when they exceed their depth limits. Comparing the Mariana Trench to other extreme environments on Earth reveals just how hostile this place really is. The peak of Mount Everest sits at an altitude where the air pressure is 1/3 of sea level, making it difficult to breathe but not instantly fatal. The 1,100 atmosphere pressure at Challenger Deep crushes steel submersibles, whereas Everest's 0.33 atmosphere pressure simply reduces breathing capacity. Even the most extreme desert environments on Earth pale in comparison to the crushing forces found at the bottom of the ocean. Space, ironically, looks like a luxury resort compared to the Mariana Trench. Astronauts on the International Space Station face the vacuum of space, which creates a pressure differential of just 1 atmosphere. The human body can survive in a vacuum for about 30 seconds before losing consciousness, and properly designed spacesuits can protect against these conditions for hours. But in the Mariana Trench, the pressure differential is 1,100 times greater than the vacuum of space, and no amount of protective equipment can shield a human body from these forces. Despite these seemingly impossible conditions, life has found a way to thrive in the Hadal Zone. The MIR project found 7,564 microbial species and 2 macrofauna with convergent adaptations. Dark, freezing, high-pressure microbes and amphipods share antioxidation and solute strategies. These microorganisms have developed unique evolutionary traits for energy intake and pressure resistance that allow them to survive at the deepest sea levels. The creatures living in this environment have evolved remarkable adaptations. Researchers have discovered an amphipeda species that thrives at depths between 6,800 to 11,000 meters, where pressure is equivalent to balancing an SUV on a fingertip. The research teams also examined 11 species of deep-sea fish that have developed genetic adaptations allowing them to survive in these extreme depths. These organisms have evolved specialized proteins that maintain their cellular structure under crushing pressure, and their metabolisms have adapted to extract energy from the limited chemical compounds available in this environment. The geology of the Mariana Trench creates additional challenges for any nuclear explosion. The trench formed at a subduction zone where the denser Pacific plate is forced beneath the smaller Mariana plate. This ongoing geological process creates a crescent-shaped depression that continues to deepen over time. The steep walls of Challenger Deep consist of sedimentary rock layers that have been compressed and folded by tectonic forces over millions of years. The seafloor itself is covered in a layer of fine sediment that has accumulated from organic matter falling from the surface waters above. Recent scientific expeditions have revealed the trench's unique chemical composition. The water at these depths contains elevated levels of dissolved minerals that have been leached from the surrounding rock under extreme pressure. The temperature remains constant at 1 to 4 degrees Celsius throughout the year, creating a stable thermal environment that contrasts sharply with the dynamic pressure conditions. The complete absence of sunlight means that no photosynthesis occurs, forcing all life forms to rely on chemosynthesis or the consumption of organic matter that drifts down from surface waters. Human exploration of the Mariana Trench remains extremely limited due to the technical challenges involved. The first descent to Challenger Deep took place on January 23, 1960, when Jacques Piccard and Don Walsh reached a depth of 10,916 meters. More recently, Canadian filmmaker James Cameron piloted the submersible deep-sea Challenger to 35,756 feet in 2012, establishing a new world record for solo descent. These expeditions required specially designed vessels capable of withstanding the crushing forces, and even then, the exploration time was limited to just a few hours. The pristine nature of the Mariana Trench makes it an ideal testing ground for our nuclear thought experiment, but recent discoveries show that even this remote location isn't completely free from human impact. Researchers have encountered plastic bags, soda cans, beer bottles, and even a laundry basket during their expeditions. This contamination demonstrates that human influence reaches even the most remote corners of our planet. No nuclear weapon has ever been tested under conditions remotely similar to those found in the Mariana Trench. The combination of extreme pressure, near-freezing temperatures, and unique chemical composition creates an environment that will fundamentally alter how our nuclear explosion behaves. The physics of nuclear detonation that apply at sea level or in the atmosphere simply don't translate to conditions where every cubic meter of space is compressed by forces equivalent to 1,100 atmospheres. This eternal darkness, crushing pressure, and alien environment sets the stage for something unprecedented. When our 50-megaton weapon arrives at the bottom of this underwater world, it will encounter forces that no nuclear engineer ever considered during the weapon's design. The microsecond that changes everything. The moment of detonation transforms the deepest point on Earth into something resembling the birth of a star. In the first microsecond, neutrons strike uranium-235 and plutonium-239 nuclei inside the weapon's core, triggering a cascading chain reaction where each fission event releases roughly 200 million electron volts of energy along with additional neutrons that trigger more splits. This process accelerates exponentially, with each generation of reactions occurring faster than the previous one. Within that first microsecond, trillions of atoms undergo fission, releasing energy equivalent to 50 million tons of TNT exploding simultaneously. The weapon's fusion stage amplifies this destruction even further. The initial fission reaction creates temperatures exceeding 100 million degrees Celsius hot, enough to force hydrogen isotopes to overcome their electromagnetic repulsion and fuse together. This fusion process releases even more energy per unit mass than fission, converting roughly 0.7% of the fuse mass directly into energy according to Einstein's equation. The result is a controlled stellar explosion happening at the bottom of Earth's deepest ocean. The first visible sign of this nuclear chaos is a brilliant flash of light that illuminates the eternal darkness of the Mariana Trench for the first time in Earth's history. This light carries every color of the electromagnetic spectrum, from radio waves to gamma rays, creating a brief moment when the deepest parts of our planet experience something resembling daylight. The photons race outward at the speed of light, carrying with them the signature of nuclear destruction. The intense heat from the nuclear reaction instantly vaporizes everything within a rapidly expanding sphere. Water molecules break apart into hydrogen and oxygen atoms, then into individual protons and electrons as temperatures reach levels found only in the cores of stars. This creates a superheated cavity filled with vaporized water, radioactive particles, and the atomized remains of any deep-sea creatures unfortunate enough to be in the immediate vicinity. The creatures living near the detonation site face an incredibly brief but spectacularly bad day. The amphipods that have spent millions of years evolving to survive crushing pressure suddenly find themselves dealing with temperatures that would instantly vaporize titanium. The specialized bacteria that have adapted to extract energy from chemical compounds at the seafloor become part of the expanding plasma cloud before they can even begin to process what's happening. Even the hardy organisms that have survived every environmental challenge the deep ocean can throw at them become radioactive vapor in nanoseconds. The initial fireball forms as this superheated cavity expands outward, driven by the immense pressure created by the nuclear reaction. In the first milliseconds, this expanding bubble of destruction contains temperatures exceeding those found at the sun's core, pressures that dwarf anything naturally occurring on Earth, and enough energy to power the entire United States for several days. The bubble's interior reaches pressures of several billion atmospheres, creating conditions that exist nowhere else in the known universe. The energy released from our 50-megaton weapon staggers the imagination. To put this in perspective, the explosion releases energy equivalent to the global electricity consumption of approximately 2.5 days compressed into a single instant. The 1980 eruption of Mount St. Helens, which devastated 600 square kilometers of forest and ejected 1.2 cubic kilometers of material, released energy equivalent to 24 megatons of TNT. Our underwater explosion contains more than double that energy, concentrated in a space smaller than a football stadium. Comparing this energy to other natural phenomena reveals the truly extraordinary nature of nuclear weapons. The most powerful earthquake ever recorded, the 1960 Chilean earthquake, released energy equivalent to approximately 178,000 megatons of TNT. However, this energy was released over several minutes and distributed across hundreds of kilometers of fault line. Our nuclear explosion concentrates similar energy densities into a microscopic point for a fraction of a second, creating conditions that exceed anything nature produces on Earth. The explosion generates a shockwave that propagates outward through the water at supersonic speeds. This shockwave carries enough energy to be detected by seismic monitoring stations around the world, registering as a significant earthquake despite originating from a man-made source. Marine animals throughout the Pacific Ocean will sense this disturbance, as whales and dolphins can detect sound waves traveling thousands of kilometers through the water. The nuclear fuel's transformation into pure energy follows the fundamental laws of physics that govern stellar formation and the birth of heavy elements in the universe. The same nuclear processes that power the sun and create the elements essential for life are now occurring at the bottom of Earth's deepest ocean. Iron, nickel, and other heavy elements that formed in the cores of ancient stars billions of years ago are now being subjected to conditions that briefly recreate those stellar environments. The expanding fireball contains radioactive isotopes that will persist for thousands of years, transforming the pristine deep-sea environment into a radioactive wasteland. Strontium-90, cesium-137, and other fission products begin their deadly journey through the ocean's food chain, carrying the signature of human destruction to every corner of the Pacific. These radioactive particles will outlast entire civilizations, serving as a permanent reminder of this moment when humanity's most destructive technology met nature's most extreme environment. As the fireball continues expanding, it faces the first real resistance from the surrounding water. The nuclear explosion's energy must now compete with the crushing pressure of 11 kilometers of water overhead, setting up a battle between human destructive power and natural forces that has never been tested before. The fireball's expansion begins to slow as it encounters water that refuses to be displaced easily, creating the first hint that this explosion won't behave like anything nuclear physicists have modeled before. The bubble's rapid expansion creates a pressure wave that races outward faster than sound can travel through water. This pressure pulse contains enough energy to crush any human-made structure. Yet it represents only the beginning of a much stranger story. The initial microsecond of destruction has created a bubble of superheated plasma that now must contend with an environment that has spent billions of years learning how to absorb and dissipate energy from asteroid impacts, volcanic eruptions, and tectonic collisions. Something unprecedented is about to happen. Our nuclear fireball, which should be expanding uncontrolled like every other nuclear explosion in history, is about to encounter a force that will fundamentally change how it behaves. When physics gets weird, the bubble battle begins. The ocean's crushing pressure transforms our nuclear explosion into something that defies conventional physics. The expanding bubble of superheated gas and vapor begins its outward journey like a freight train with no brakes, vaporizing everything in its path. The bubble wall moves faster than the speed of sound in saltwater, creating a supersonic expansion that tears through the water at roughly 1,500 meters per second. This isn't just fast. It's impossibly fast for anything moving through water at these depths. The bubble contains vaporized water molecules, radioactive particles, and what used to be deep-sea organisms, all mixed together in a hellish cocktail of destruction moving outward at speeds that would make a bullet look sluggish. The shockwave that accompanies this expansion carries enough energy to register on seismic monitoring stations across the globe. Scientists in Japan, California, and Alaska will detect this underwater explosion as a significant earthquake, despite knowing that no natural geological activity occurred in the Mariana Trench. The pressure pulse travels through the Pacific Ocean at speeds approaching 5 kilometers per second, creating a signature that marine seismologists will recognize immediately as artificial. Whales migrating thousands of kilometers away will sense this disturbance through their specialized acoustic organs, suddenly finding their underwater communication networks disrupted by the most powerful sound ever produced in the ocean. In a surface explosion, this fireball would continue expanding unimpeded until it reaches a diameter of 10 kilometers within the first few seconds. The atmosphere provides almost no resistance to the expanding gases, allowing the nuclear fireball to grow into the familiar mushroom cloud that rises dozens of kilometers into the sky. The air molecules simply get pushed aside as the explosion expands, creating the characteristic dome of destruction that levels everything within a massive radius. But our underwater explosion faces a completely different reality. The ocean doesn't just get pushed aside, it pushes back with the force of 11 kilometers of water pressing down from above. This creates a fundamental conflict between the explosive force trying to expand outward and the crushing pressure trying to contain it. The water acts like an invisible force field that refuses to yield to our nuclear intrusion, creating resistance that grows exponentially stronger as the bubble tries to expand. The ocean essentially tells our nuclear weapon to sit down and behave like a civilized explosion. After spending billions of years absorbing energy from asteroid impacts, volcanic eruptions, and tectonic collisions, the ocean has developed an almost supernatural ability to contain and dissipate massive amounts of energy. Our 50-megaton bomb represents nothing more than Tuesday afternoon entertainment for a body of water that has been dealing with planetary-scale disasters since the formation of Earth. The growing tension between explosive force and water pressure creates a battle that has never been witnessed in human history. The bubble's initial expansion generates pressures measured in billions of atmospheres, yet this still isn't enough to overcome the crushing forces surrounding it. The water pressure acts like a cosmic-sized hydraulic press, squeezing the explosion from every direction simultaneously. Every cubic meter of space around the detonation point experiences forces equivalent to having multiple skyscrapers stacked on top of it. This pressure differential creates something that nuclear physicists have never observed in real-world conditions. The bubble's expansion slows dramatically as it encounters water that refuses to be displaced easily. The smooth expansion that characterizes surface explosions gives way to turbulent instabilities that create fractal patterns along the bubble wall. Cold ocean water begins forming finger-like projections that extend into the superheated bubble, creating a chaotic mixing process that fundamentally alters the explosion's behavior. The bubble wall develops what researchers call Rayleigh-Taylor instability, where the interface between the hot gas and cold water becomes increasingly turbulent. This creates a complex pattern of fingers and branches that look like underwater lightning, with cold seawater penetrating deeper into the bubble, while hot gas simultaneously tries to expand outward. The mixing process causes the gas temperature to drop rapidly as it comes into contact with near-freezing ocean water, reducing the internal pressure that drives the expansion. Something unprecedented is happening that defies every model of nuclear explosion physics. The bubble's expansion rate decreases exponentially as the water pressure begins winning the battle for dominance. Nuclear weapons are designed to create maximum destruction through rapid expansion and energy release, but the Mariana Trench environment is systematically neutralizing these advantages. The crushing depths are forcing our explosion to operate under physical constraints that simply don't exist in surface detonations. The bubble reaches its maximum diameter of approximately 1 kilometer after the first second, at which point the expansion stops entirely. This represents a fraction of what the same explosion would achieve in the atmosphere, where the fireball will continue growing to 10 times this size. The water pressure has effectively capped the explosion's expansion potential, creating a situation where the most powerful nuclear weapon ever built is being constrained by simple hydrostatic pressure. The nuclear explosion that was designed to level entire cities is now struggling to maintain its basic structure against the crushing forces of the deep ocean. The bubble begins to lose internal pressure as it expands, following the basic gas laws that govern how pressure and volume relate to each other. As the bubble grows larger, the gas inside becomes less dense and the pressure drops accordingly. This pressure reduction gives the surrounding water an advantage in the ongoing battle for territorial control. The ocean's victory becomes apparent as the bubble's expansion not only stops but begins to reverse. The water pressure starts compressing the bubble back towards original size, creating the first stage of what will become a deadly cycle of expansion and contraction. The explosive force that was supposed to create unstoppable destruction is now being systematically defeated by the same water pressure that allows deep-sea creatures to survive at these depths. Our unstoppable nuclear force is about to discover what happens when physics decides to run an explosion in reverse. The Great Compression, when explosions go backwards. The water pressure begins its systematic dismantling of our nuclear explosion through a process that defies every expectation about how weapons of mass destruction behave. The expanding fireball reaches its maximum size of approximately 1 kilometer in diameter after the first second, at which point something unprecedented happens. The bubble suddenly begins shrinking, actively compressing back towards its original size in a complete reversal of nuclear explosion physics. This compression occurs because the expanding bubble overextends itself, losing internal pressure as it grows larger according to basic gas laws. As the bubble expands, the gas inside becomes less dense and the internal pressure drops accordingly. Meanwhile, the crushing water pressure surrounding the explosion maintains constant force from every direction. Eventually, the external pressure overcomes the internal pressure, and the bubble begins collapsing back towards original size. Think of this process like a balloon being squeezed by a hydraulic press that operates in 3 dimensions simultaneously. The balloon starts small and tight, then inflates rapidly under internal pressure. But as it expands, the material stretches thinner and the internal pressure decreases. The hydraulic press maintains constant pressure from every direction until the external pressure overcomes the internal pressure, forcing the balloon to collapse. Our nuclear explosion faces exactly this scenario, except the hydraulic press consists of 11 kilometers of crushing ocean water. The nuclear weapon essentially gets performance anxiety under pressure, failing to maintain its explosive expansion when faced with environmental conditions it was never designed to handle. Nuclear weapons work by creating maximum destruction through rapid expansion and energy release, but the Mariana Trench environment systematically neutralizes these advantages. The crushing depths force our explosion to operate under physical constraints that simply don't exist in surface detonations where nuclear weapons normally prove their destructive capabilities. The water pressure begins winning this tug-of-war through sheer persistence and overwhelming force. Every cubic meter of space around the detonation point experiences forces equivalent to having multiple skyscrapers stacked on top of it, creating a compression effect that grows stronger as the bubble tries to expand. The water doesn't just resist the explosion, it actively pushes back with increasing force, creating a dynamic where the bubble's own expansion works against its ability to maintain internal pressure. The bubble shrinkage occurs just as rapidly as its initial expansion, creating a compression cycle that happens faster than the human eye could follow. The superheated gas and vapor that moments before were expanding at supersonic speeds now find themselves being compressed back toward their original volume. This compression heats the gas even further, temporarily increasing the internal pressure and causing the bubble to expand again. The result is a deadly oscillation where the bubble alternately grows and shrinks in a repeating cycle. This oscillation pattern creates multiple cycles of expansion and compression that become progressively weaker with each repetition. The bubble expands, reaches its maximum size, then contracts under water pressure. The compression heats the gas, causing another expansion, followed by another compression. Each cycle dissipates more energy than the previous one, as the bubble loses heat to the surrounding water and the turbulent mixing processes that occur at the bubble's boundary. The multiple expansion and compression cycles create a complex pattern of energy dissipation that fundamentally alters the explosion's behavior. Each oscillation transfers energy from the nuclear explosion to the surrounding water through heat conduction, turbulent mixing, and the work required to displace massive amounts of water. The bubble's surface area becomes a battleground where superheated gas meets near freezing ocean water, creating temperature gradients that drive rapid energy transfer. Cold ocean water begins forming finger-like projections that extend into the superheated bubble during each compression cycle, creating what researchers call Rayleigh-Taylor instability. These fingers of cold water penetrate deeper into the bubble with each oscillation, increasing the surface area between hot gas and cold water. The increased contact area accelerates the cooling process, causing the gas temperature to drop and the internal pressure to decrease more rapidly. The bubble's oscillation period depends on the water pressure and the size of the blast, with deeper explosions having slightly longer oscillations due to the increased pressure differential. The expansion quickly becomes unsustainable because the amount of water pushed outward increases with the cube of the blast bubble radius, creating exponentially greater resistance as the bubble tries to grow larger. This mathematical relationship ensures that the bubble's expansion capabilities decrease rapidly with each cycle. The energy dissipation process accelerates as the bubble loses heat to the surrounding water through multiple mechanisms simultaneously. The turbulent mixing at the bubble boundary creates microscopic eddies that increase the heat transfer rate. The phase change from steam back to liquid water absorbs enormous amounts of energy, further cooling the bubble's interior. The work required to displace increasingly large volumes of water drains energy from the expansion process. Our mighty nuclear weapon is being systematically defeated by simple water pressure, demonstrating that even humanity's most destructive creation cannot overcome the fundamental forces that govern planetary physics. The ocean's victory becomes more apparent with each oscillation cycle, as the bubble's maximum size decreases and the compression phases become more pronounced. The weapon that was designed to level entire cities is being reduced to a series of underwater hiccups by the same water pressure that allows deep-sea creatures to survive at these depths. The final oscillation grows weaker as the bubble's remaining energy proves insufficient to overcome the crushing forces that surround it. The expansion phase becomes shorter and less dramatic, while the compression phase grows longer and more complete. The nuclear explosion that began with the power to vaporize Manhattan is now struggling to maintain even a fraction of its original size against the relentless pressure of the deep ocean. The bubble's defeat appears inevitable as it faces one final, decisive compression that will determine whether any trace of our nuclear destruction can survive the crushing depths of the Mariana Trench, the underwater mushroom cloud that wasn't. The collapse marks the end of nuclear physics and the beginning of underwater chaos. After multiple cycles of expansion and compression, the fireball reaches the point where its remaining energy simply cannot overcome the crushing forces surrounding it. The water pressure has systematically drained the explosion's power through repeated oscillations, heat transfer, and the enormous work required to displace massive amounts of water. The bubble's final collapse represents the moment when 50 megatons of nuclear energy surrenders to the simple physics of hydrostatic pressure. The final collapse unfolds as water pressure overwhelms the explosion's remaining energy reserves. The bubble contracts one last time, but this compression doesn't generate enough heat to trigger another expansion cycle. Instead, the superheated gas and vapor find themselves being squeezed into an increasingly smaller volume while losing temperature to the surrounding near-freezing water. The nuclear explosion that began with temperatures exceeding those found in stellar cores now faces the reality of being cooled by ocean water that hovers just above freezing. Turbulent water begins chopping up the bubble into smaller radioactive fragments during this final collapse. The smooth spherical surface that characterized the initial fireball breaks apart into chaotic patterns as cold seawater penetrates deeper into the bubble's interior. These intrusions create what researchers call Rayleigh-Taylor instability, where fingers of cold water extend into the hot gas while simultaneously creating pockets of superheated material that become isolated from the main bubble. The result is a fragmentation process that transforms one large bubble into hundreds of smaller ones, each carrying its own payload of radioactive material. The smaller bubbles that emerge from this fragmentation process look nothing like the traditional mushroom cloud that defines surface nuclear explosions. Instead of a single massive plume rising majestically into the sky, we get a chaotic collection of radioactive bubbles drifting upward through the water column like the world's most dangerous lava lamp. These fragments contain vaporized water, radioactive particles, and the atomized remains of deep-sea creatures, all mixed together in a hellish cocktail that begins its slow journey toward the surface. This represents the most anticlimactic end to a nuclear explosion in human history. Hollywood has conditioned us to expect massive mushroom clouds, devastating shockwaves, and immediate widespread destruction. Instead, our 50-megaton weapon produces what can only be described as underwater burping. The most powerful nuclear weapon ever created by humanity has been reduced to a series of radioactive bubbles that look more like a failed science experiment than an instrument of mass destruction. The smaller bubbles begin their journey toward the surface, carrying radioactive material through 11 kilometers of water. These fragments rise slowly due to their lower density compared to the surrounding seawater, but their ascent is far from uniform. Some bubbles combine with others during their upward journey, creating larger fragments that rise faster. Others break apart further, creating even smaller bubbles that drift upward at different rates. The result is a complex pattern of radioactive dispersion that spreads throughout the water column. The long journey upward through 11 kilometers of water takes considerable time for these radioactive fragments to complete. The bubbles must travel through different pressure zones, temperature gradients, and water densities as they rise from the abyssal depths toward the surface. This journey allows significant cooling and mixing with the surrounding seawater, which dilutes the radioactive concentration and reduces the temperature of the rising material. The bubbles that began their journey as superheated gas gradually cool to match the temperature of their surroundings. During this ascent, the radioactive bubbles interact with the complex ecosystem of the Pacific Ocean. Deep-sea creatures that normally migrate vertically through the water column encounter these radioactive fragments at various depths. Fish, squid, and other marine organisms become inadvertent participants in the dispersal process either by direct contact with the radioactive material or through the food chain connections that link different ocean depths. The contamination spreads through biological pathways that extend far beyond the immediate blast zone. The pressure changes that occurred during the upward journey cause the bubbles to expand as they rise, following the basic gas laws that govern how volume and pressure relate to each other. Bubbles that started small at the bottom of the trench grow larger as they encounter decreasing pressure at higher depths. This expansion process continues until the bubbles reach the surface, where they finally escape the crushing pressure that has dominated their behavior since the initial detonation. Marine life in the upper water column experiences the first signs of the ascending radioactive plume. Plankton, small fish, and other organisms that form the base of the ocean food web encounter radioactive particles that have been dispersed throughout the water column. These microscopic organisms begin incorporating radioactive isotopes into their cellular structures, starting a contamination process that will eventually affect larger predators and ultimately impact the entire marine ecosystem. The surface tension of the Pacific Ocean provides the final barrier that these radioactive bubbles must overcome. As the fragments approach the surface, they encounter the interface between water and air, where different physical properties create the last obstacle in their journey from the deepest part of the ocean to the atmosphere. The bubbles must have sufficient buoyancy and momentum to break through this surface tension and release their radioactive contents into the air above. After all this drama, the surface effect proves surprisingly mundane. The emergence of radioactive bubbles at the surface creates nothing more than some bubbling and a small wave that would barely register on any seismic equipment. The Pacific Ocean simply produces a brief disturbance that looks like a natural underwater gas seep or a small volcanic vent releasing trapped gases. The anticlimactic nature of this surface event stands in stark contrast to the massive destruction that the same weapon would have produced if detonated at ground level. The small wave that spreads outward from the emergence point carries radioactive material across the surface of the Pacific Ocean, beginning the next phase of contamination. But this modest disturbance raises an obvious question about the catastrophic consequences that most people expect from underwater nuclear explosions, the tsunami that never came. Popular culture has convinced millions of people that underwater nuclear explosions automatically generate devastating tsunamis, but the physics of wave formation tell a completely different story. This misconception stems from decades of disaster movies that prioritize dramatic visual effects over scientific accuracy, creating expectations of massive walls of water that devastate entire continents when the reality proves far more mundane. Tsunamis required the vertical displacement of enormous volumes of water to generate the long wavelength waves that can travel across entire ocean basins. This displacement typically occurs when underwater earthquakes cause massive sections of seafloor to suddenly shift upward or downward, forcing billions of tons of water to move accordingly. Volcanic eruptions create similar effects when they eject huge amounts of material into the ocean or cause underwater landslides that displace water masses. These geological events create sustained, large-scale water displacement that propagates outward in all directions. Nuclear explosions work through completely different mechanisms that don't efficiently translate into tsunami generation. The energy from our 50-megaton weapon gets released as a rapidly expanding bubble of superheated gas that undergoes repeated cycles of expansion and compression. This process dissipates the majority of the explosion's energy through heat transfer and turbulent mixing rather than creating the sustained vertical water displacement necessary for tsunami formation. The explosion creates a powerful shockwave that travels through the water, but the shockwave doesn't produce the massive water displacement that characterizes tsunami-generating events. The depth of the water at the point of detonation significantly influences the potential for tsunami formation, with deeper explosions being less likely to trigger large waves. This occurs because the energy from the explosion is more readily absorbed and dispersed by the surrounding water at greater depths, reducing the efficiency of wave generation. The extreme pressure at the bottom of the Mariana Trench essentially fights back against the nuclear intrusion, constraining the explosion's ability to create sustained water displacement. Recent tsunami modeling data reveals just how dramatically reality differs from Hollywood expectations. Computer simulations show that our underwater nuclear explosion would produce surface waves measuring only a few meters in height, concentrated in the immediate vicinity of the detonation point. These waves would dissipate rapidly as they spread outward, losing energy through friction and dispersion. The wave height decreases exponentially with distance from the explosion site, meaning that even nearby islands would experience waves no larger than those generated by moderate storms. Actual tsunami-generating events like underwater earthquakes and volcanic eruptions operate through mechanisms that create far more efficient water displacement than nuclear explosions. The 2004 Indian Ocean tsunami was generated by a magnitude 9.1 earthquake that caused a 1,600-kilometer section of seafloor to shift vertically by approximately 15 meters. This massive geological displacement moved trillions of tons of water simultaneously, creating waves that maintain their energy across thousands of kilometers of ocean. The 2011 tsunami that struck Japan originated from a magnitude 9.0 earthquake that displaced enormous sections of the Pacific seafloor, generating waves that reach heights of 40 meters in some coastal areas. Compare these massive geological events to our nuclear explosion, which creates a temporary bubble that quickly loses energy to the surrounding water. The explosion might vaporize millions of tons of water initially, but this vaporization doesn't create the sustained displacement necessary for tsunami generation. The bubble's oscillations actually work against tsunami formation by dissipating energy through repeated expansion and compression cycles rather than transferring energy efficiently into propagating waves. Boats and marine life in the immediate area would experience something far different from the catastrophic tsunamis portrayed in popular culture. Vessels within a few kilometers of the detonation site would encounter powerful shock waves that could cause structural damage or capsizing, but these effects would be localized rather than part of a widespread tsunami. The pressure waves would create sudden changes in water density and temperature that would disorient marine animals and potentially cause injury to sensitive species like whales and dolphins. Fish populations in the immediate vicinity would face the dual threats of pressure trauma and thermal shock as the explosion's energy propagates through the water column. The immediate surface effects of our deep underwater nuclear explosion would be surprisingly mundane compared to the dramatic expectations created by disaster films. The expanding and contracting bubble eventually fragments into smaller, radioactive bubbles that rise to the surface over several hours. The result is a small wave measuring perhaps 10 meters in height at most, accompanied by a bubbling plume of warm, radioactive water that looks more like a natural underwater gas seep than a catastrophic nuclear event. While coastal populations can breathe easy knowing that no tsunami apocalypse threatens their cities, the absence of massive waves doesn't mean our underwater nuclear explosion lacks consequences. The radioactive contamination that emerges from the fragmented bubble represents a more subtle but persistent threat that will affect marine ecosystems for decades. The contaminated water doesn't simply disappear after reaching the surface. It begins a complex journey through the Pacific Ocean that follows predictable patterns based on current flows and seasonal variations. The Pacific Ocean circulation patterns will carry this radioactive material across vast distances, dispersing it through biological pathways and ocean currents that affect marine ecosystems far beyond the immediate blast zone. Some of this contaminated water will eventually evaporate into the atmosphere, carrying radioactive particles into weather systems that could affect regions thousands of kilometers from the original detonation site. The question becomes not whether massive tsunamis will devastate coastal cities, but rather how this radioactive contamination will spread through the interconnected systems that govern our planet's oceans and atmosphere. Radioactive rain and ocean dilution. The radioactive contamination follows predictable pathways through the Pacific Ocean circulation system, beginning its journey as part of the North Pacific subtropical gyre. This vast clockwise rotating current system spans thousands of kilometers and acts like a giant washing machine, mixing radioactive particles with billions of tons of seawater as it slowly rotates across the Pacific. The contaminated water becomes part of a massive conveyor belt system that never stops moving, carrying our nuclear legacy across the world's largest ocean. The radioactive particles begin their journey by following the dominant surface currents that flow eastward from the Mariana Trench toward the Americas. The Kuroshio current, often called the Pacific's Gulf Stream, would carry contaminated water northward along the Japanese coast before merging with the North Pacific Current. This eastward flowing current system would transport radioactive material across the entire Pacific Ocean over the course of several years, eventually reaching the coastlines of California, Oregon, and Washington. Ocean currents and dilution work together to spread contamination across enormous distances while simultaneously reducing its concentration. The Pacific Ocean contains roughly 710 million cubic kilometers of water, providing an almost incomprehensible amount of liquid to dilute our radioactive materials. As the contaminated water mixes with this vast volume, the concentration of radioactive isotopes decreases exponentially. However, the total amount of radioactive material remains constant as it spreads across larger areas, meaning the contamination persists even as it becomes more diluted. The 2025 oceanographic data reveals complex dispersion patterns that depend on seasonal variations and climate change effects. Computer models show that contaminated water would initially move in predictable patterns following established current flows, but these patterns shift throughout the year as ocean temperatures and wind patterns change. Winter storms in the North Pacific would accelerate the mixing process, while summer conditions would create more stable layering that keeps contaminated water at specific depths. Some radioactive material makes it into the atmosphere through evaporation processes that occur at the ocean surface. As waves break and winds blow across the contaminated water, microscopic droplets containing radioactive particles become airborne. These particles then travel through the atmosphere according to prevailing wind patterns, potentially reaching land masses thousands of kilometers from the original detonation site. The process essentially creates the world's most expensive and dangerous hot tub, where every bubble that pops releases radioactive steam into the air. The evaporation process becomes more significant as contaminated water spreads across larger surface areas. The sun's energy drives constant evaporation from the ocean surface, and radioactive particles small enough to remain suspended in water droplets can become airborne through this natural process. Trade winds and storm systems then carry these airborne particles across the Pacific, potentially depositing them through precipitation far from the original explosion site. Radioactive rainfall occurs when these airborne particles encounter weather systems that produce precipitation. The radioactive particles act as condensation nuclei, helping water vapor form droplets that eventually fall as rain. This process means that areas experiencing weather systems that originated over contaminated ocean areas could receive radioactive precipitation. The Hawaiian Islands, for example, would likely experience some level of radioactive rainfall within months of the explosion, due to their position in the Pacific trade wind belt. The geographic distribution of radioactive rainfall depends heavily on seasonal weather patterns and the specific atmospheric conditions at the time of dispersion. Winter storm systems in the North Pacific would carry radioactive particles toward the west coast of North America, while summer conditions might direct contamination toward different regions. The jet stream's position and strength would influence how far radioactive particles travel through the atmosphere before being deposited through precipitation. Marine ecosystems face significant environmental impacts from this radioactive contamination, starting with the microscopic organisms that form the foundation of ocean food webs. Plankton, which include both phytoplankton that photosynthesize and zooplankton that feed on other organisms, would incorporate radioactive isotopes directly into their cellular structures. These contaminated organisms then become food for small fish, which are eaten by larger fish, creating a bioaccumulation process that concentrates radioactive materials in top predators. The deep-sea environment of the Mariana Trench hosts unique ecosystems that have never been exposed to artificial radiation. A 2025 study revealed an unprecedented level of taxonomic novelty, with 89.4% of identified microbial species previously unreported in the Mariana Trench. These newly discovered organisms have evolved specialized adaptations for surviving extreme pressure and limited food sources, but they have no evolutionary defenses against radioactive contamination. The study showed that selection pressures, favoring either streamlined or versatile adaptation strategies, dominate over neutral drift in shaping these extreme microbial ecosystems, which could be fundamentally altered by radiation exposure. Recent studies on radioactive contamination in ocean environments demonstrate that marine organisms concentrate certain isotopes in specific tissues. Cesium-137 tends to accumulate in muscle tissue, while strontium-90 concentrates in bones and shells. These patterns mean that different species face varying levels of risk depending on their physiology and feeding habits. Filter-feeding organisms like mussels and clams would face immediate exposure as they process contaminated water, while deep-sea predators would accumulate radioactive materials to their prey over longer periods. The long-term effects of radioactive contamination on marine ecosystems extend far beyond the immediate blast zone. Fish populations could experience genetic mutations that affect reproduction rates and survival capabilities. Coral reefs, despite being far from the Mariana Trench, could eventually encounter contaminated water through the Pacific circulation patterns. The contamination could disrupt the delicate symbiotic relationships between corals and the algae that provide them with nutrients through photosynthesis. Ocean dilution provides some protection against the most severe contamination effects, but it doesn't eliminate the risks entirely. The vast volume of the Pacific Ocean means that radioactive concentrations would drop to levels that might not cause immediate death in marine organisms. However, chronic exposure to low levels of radiation can cause genetic damage, reproductive problems, and increased cancer rates in marine life. The effects would be most pronounced in species with longer lifespans and those that occupy higher positions in the food web. The dilution effect means the impact is more localized and global, but still significant for marine life in the immediate area and along the contamination pathway. Areas within several hundred kilometers of the explosion site would experience the highest levels of contamination, while distant regions would face much lower but still measurable radioactive exposure. The contamination would persist in the marine environment for decades, with some isotopes remaining hazardous for hundreds of years. Despite the ocean's enormous capacity for dilution, the introduction of artificial radioactive materials would leave a lasting signature in Pacific marine ecosystems that scientists could detect for generations. But what about the more dramatic geological consequences that most people expect from such a massive explosion? Earthquakes, volcanoes, and geological disappointment. The geological consequences prove far less dramatic than popular imagination suggests. Surely our nuclear weapon would at least trigger some devastating earthquakes or volcanic eruptions? After all, we're detonating 50 megatons of explosive power directly at the boundary between two tectonic plates in one of the most geologically active regions on Earth. The Mariana Trench sits at a subduction zone where the Pacific Plate slides beneath the Philippine Sea Plate, creating what seems like perfect conditions for triggering massive geological catastrophes. The reality of why detonating at tectonic plate boundaries doesn't automatically trigger geological catastrophes lies in understanding the massive scale of forces involved in natural geological processes. Tectonic plates move with incredible power, but they operate on timescales measured in millions of years and energy levels that dwarf anything humans can produce. The collision between oceanic plates that created the Mariana Trench involves forces equivalent to millions of nuclear weapons operating continuously over geological time. Our single 50-megaton explosion represents a tiny hiccup in processes that have been operating for tens of millions of years. The 2025 seismic data reveals just how insignificant nuclear explosion energy appears when compared to natural earthquake energy. The most powerful earthquake ever recorded, the 1960 Chilean earthquake, released energy equivalent to approximately 178,000 megatons of TNT. This energy was distributed across hundreds of kilometers of fault line and released over several minutes, creating devastating effects that were felt across the entire Pacific Ocean. Our nuclear weapon contains only 50 megatons of energy released in a single instant at one specific point, making it roughly 3,500 times less powerful than this natural earthquake. Most of the energy from our underwater nuclear explosion goes into vaporizing water rather than creating seismic waves that could trigger geological events. The extreme pressure at the bottom of the Mariana Trench forces the explosion to expend enormous amounts of energy just to displace the surrounding water. The process of converting liquid water into superheated steam requires massive energy input, and this energy conversion absorbs a majority of the explosion's power. The remaining energy that could potentially create seismic waves gets dissipated through the water column rather than being transmitted efficiently into the solid rock of the seafloor. Earth demonstrates remarkable geological indifference to human destructive efforts, treating our most powerful weapons like minor inconveniences rather than existential threats. The planet has survived asteroid impacts that released energy equivalent to millions of nuclear weapons, volcanic eruptions that changed global climate patterns, and tectonic collisions that created entire mountain ranges. Our nuclear explosion represents nothing more than a brief thermal event in an environment that routinely experiences far more dramatic energy releases through natural processes. The seismic energy of our bomb compares poorly to earthquakes that happen naturally several times per year around the world. Magnitude 7.0 earthquakes, which occur approximately 15 times annually, each release energy equivalent to roughly 32 megatons of TNT. These natural events happen regularly without triggering global catastrophes or destabilizing Earth's geological systems. A magnitude 8.0 earthquake, which occurs about once per year, releases energy equivalent to 1,000 megatons of TNT. Even these powerful natural events typically produce only localized effects, demonstrating that our 50-megaton explosion lacks the energy necessary to trigger widespread geological disruption. The misconception about nuclear weapons affecting Earth's orbit reveals perhaps the most dramatic overestimation of human destructive capability. The idea that any human-created explosion could alter Earth's orbital mechanics ignores the fundamental physics of planetary motion and the enormous forces required to change orbital trajectories. Earth's orbit results from a delicate balance between gravitational attraction to the Sun and the planet's momentum, maintained by forces that operate on scales incomprehensible to human experience. The 2,000-plus nuclear tests conducted since 1945 provide compelling evidence against any orbital impact from nuclear weapons. These tests included atmospheric detonations, underground explosions, and underwater tests that release combined energy equivalent to hundreds of thousands of megatons of TNT. Despite this massive cumulative energy release, Earth's orbit has remained completely unchanged. Precision satellite measurements and astronomical observations show no deviation from predicted orbital patterns, demonstrating that even sustained nuclear testing over decades produces no measurable effect on planetary motion. The mathematical reality of orbital mechanics makes it clear why nuclear weapons cannot affect Earth's orbit. Earth's orbital velocity around the Sun averages 29.78 kilometers per second, maintained by the planet's kinetic energy of approximately 2.6 times 10 to the power of 33 joules. Our 50-megaton nuclear weapon releases roughly 2.1 times 10 to the power of 17 joules of energy, making it about 12 trillion times too small to produce any meaningful change in Earth's orbital energy. Even if all the world's nuclear weapons were detonated simultaneously, they would release less than 0.0000001% of the energy required to alter Earth's orbit by any measurable amount. Volcanic activity operates through complex geological processes that our nuclear explosion cannot significantly influence. Volcanic eruptions result from the buildup of magma pressure over thousands of years, driven by heat from Earth's interior and the slow movement of tectonic plates. The mechanisms that trigger volcanic eruptions involve pressure differentials, gas content in magma, and structural weaknesses in the Earth's crust that develop over geological timescales. Our brief nuclear explosion lacks the sustained energy input and specific geological conditions necessary to trigger volcanic activity. The planet's immense size and inherent stability render it largely impervious to nuclear detonation effects. Earth's mass of approximately 5.97 times 10 to the power of 24 kilograms creates gravitational forces that maintain geological stability against all but the most extreme events. The energy required to cause significant geological disruption must be sustained over long periods or concentrated in ways that exploit existing geological weaknesses. Our nuclear explosion provides neither sustained energy input nor the specific targeting of geological vulnerabilities that would be necessary to trigger major earthquakes or volcanic eruptions. The strongest forces humanity can unleash remain laughably small compared to natural geological forces. Mountain building processes involve pressures and temperatures that dwarf anything achievable through nuclear weapons. The formation of the Himalayan mountain range continues to release energy equivalent to millions of nuclear weapons annually through ongoing tectonic collision. Ocean floor spreading along mid-ocean ridges involves continuous energy release that exceeds our nuclear weapons power by factors of millions. Earth is simply too massive and stable to be significantly affected by even our most powerful weapons. This raises a fundamental question about the relationship between human technological achievement and the natural forces that govern our planet. The humbling reality check. Our underwater nuclear experiment forces us to confront an uncomfortable truth about human technological achievement versus planetary forces. After watching our most destructive weapon get systematically dismantled by simple water pressure, we must acknowledge that the ocean essentially shrugs off our most powerful creation, like it's dealing with a minor inconvenience rather than humanity's greatest achievement in destructive capability. The complete findings from our underwater nuclear test paint a picture that challenges every assumption about human technological supremacy. Our 50-megaton hydrogen bomb, capable of leveling entire cities and irradiating thousands of square kilometers, gets reduced to underwater burping by the crushing depths of the Mariana Trench. The weapon that could vaporize Manhattan becomes nothing more than a series of radioactive bubbles drifting slowly toward the surface. The explosion that was supposed to create devastation on a planetary scale produces waves smaller than those generated by moderate storms. The 2025 data on nuclear weapons provides sobering context for understanding just how insignificant our destructive capabilities appear when measured against natural forces. The global nuclear arsenal consists of approximately 12,331 warheads, with the United States and Russia possessing about 88% of the total inventory. If every single one of these weapons were detonated simultaneously, they would release combined energy equivalent to roughly 600,000 megatons of TNT. This represents the absolute pinnacle of human destructive power, accumulated over decades of technological advancement and military spending. Yet even this massive arsenal pales in comparison to the energy released by common natural phenomena. A single major hurricane releases energy equivalent to approximately 600,000 megatons of TNT every single day. It remains active. Hurricane Katrina, which devastated New Orleans in 2005, released energy equivalent to detonating a 10-megaton nuclear weapon every 20 minutes for the entire duration of its existence. The 1815 eruption of Mount Tambora released energy equivalent to roughly 800,000 megatons of TNT, exceeding the entire global nuclear arsenal while simultaneously ejecting enough material into the atmosphere to cause global climate change. The comparison becomes even more stark when considering the energy scales involved in geological processes. The 2004 Indian Ocean earthquake that triggered the devastating tsunami released energy equivalent to 23,000 megatons of TNT in just a few minutes. The ongoing collision between the Indian and Eurasian plates that continues building the Himalayan mountain range releases energy equivalent to millions of nuclear weapons annually through continuous tectonic activity. These geological processes operate on timescales measured in millions of years, demonstrating sustained energy release that makes human weapons look like firecrackers. Humans have somehow convinced themselves that they can significantly impact a planet that regularly survives asteroid impacts, massive volcanic eruptions, and tectonic collisions that reshape entire continents. The Chicxulub asteroid impact that contributed to the extinction of the dinosaurs 66 million years ago released energy equivalent to roughly 100 million megatons of TNT. This single impact created a crater 180 kilometers wide and temporarily turned the entire planet into a molten hellscape. Yet Earth recovered, life adapted, and the planet continued its orbital journey as if nothing had happened. The Yellowstone supervolcano eruption that occurred 640,000 years ago ejected 1,000 cubic kilometers of material and released energy equivalent to several million megatons of TNT. The eruption created a caldera 85 kilometers long and 45 kilometers wide, while simultaneously altering global climate patterns for decades. The planet absorbed this massive energy release, adapted to the changing conditions, and continued supporting life throughout the crisis. Our nuclear weapons represent tiny perturbations compared to these natural catastrophes that Earth experiences regularly throughout geological history. Understanding these comparisons fundamentally changes our perspective on both nuclear weapons and natural systems. Nuclear weapons remain terrifyingly destructive to human civilization, capable of ending modern society and causing immense suffering to billions of people. The humanitarian consequences of nuclear warfare would be catastrophic for human populations, destroying cities, contaminating vast areas, and potentially triggering global conflicts that could last for generations. These weapons represent an existential threat to human survival that demands serious attention and careful management. However, the planet itself remains largely indifferent to our most powerful creations. Earth has survived billions of years of cosmic bombardment, volcanic catastrophes, and climate changes that make human activity look insignificant by comparison. The planet's ability to absorb and dissipate enormous amounts of energy ensures that even our most destructive weapons cannot fundamentally alter Earth's basic systems or knock it off its orbital trajectory. Recent scientific studies on planetary resilience reveal that Earth's systems possess remarkable ability to recover from extreme disruptions. The carbon cycle, ocean circulation patterns, and atmospheric chemistry all demonstrate self-regulating mechanisms that operate on timescales far longer than human civilization. These systems have survived multiple mass extinction events, ice ages, and periods of extreme volcanic activity while maintaining the basic conditions necessary for life to persist and evolve. The relationship between human technology and planetary forces becomes clear when viewed through this lens. We exist as a relatively recent addition to Earth's long history, wielding technological capabilities that seem impressive on human scales but remain negligible compared to the forces that shape planetary evolution. Our nuclear weapons represent the peak of human technological achievement, yet they cannot overcome the basic physics of water pressure, ocean circulation, or tectonic activity. This creates a profound sense of awe about the power of natural systems that operate continuously around us. The ocean currents that transport heat around the planet, the tectonic processes that create mountains and ocean basins, and the atmospheric circulation patterns that drive weather systems all demonstrate energy scales that dwarf human capabilities. These natural systems work together to maintain Earth's habitability while simultaneously demonstrating the planet's resilience against disruption. The implications extend beyond simple comparisons of energy output to fundamental questions about human impact on planetary systems. Climate change represents a more significant long-term threat to Earth's systems than nuclear weapons, not because individual human actions are more powerful than nuclear explosions, but because sustained human activity over decades can alter atmospheric chemistry in ways that affect global climate patterns. The cumulative effect of billions of people burning fossil fuels creates changes that persist for centuries, demonstrating that sustained human activity can influence planetary systems in ways that brief intense explosions cannot. While nuclear weapons remain terrifyingly destructive to human civilization, our underwater experiment reveals something profound about the relationship between human power and the natural world that has shaped our planet for billions of years. This experiment demonstrates that even our most advanced weapons operate within strict physical boundaries imposed by planetary systems. Our nuclear weapon versus the Mariana Trench reveals the limits of human power against natural forces that have operated for billions of years. Understanding these boundaries changes how we view both nuclear weapons and environmental protection. While our most destructive creations remain terrifyingly dangerous to human civilization, they cannot fundamentally alter the planetary forces that shape Earth's geology, climate, and ecosystems. This perspective should inspire respect for natural systems rather than attempts to dominate them. The ocean that effortlessly contained our nuclear explosion also regulates global climate, supports marine ecosystems, and maintains the delicate balance that makes life possible on our planet.